a binomial expansion. So a binomial is an expression which contains two terms. Bi meaning two, nomial meaning terms, loosely. The most simplest of them all, I guess, is that one. 1 plus x to the power of 0, which of course is 1, because anything to the power of 0 is 1. And then if we raise it to the power of 1, we get 1 plus 1x. Now, of course, I don't normally write 1x. We normally write just x, but I'm leaving the coefficient there so we can pick up on a pattern. We also know our perfect square there, so 1 plus 2x plus 1x squared. And we, from that, can get our cubic. So 1 plus 3x plus 3x squared plus x cubed. I could multiply by 1 plus x again, and we get our expansion for our quartic. And as at this point we go, oh, hang on a sec, there's a bit of a pattern here looking at those coefficients. Now that pattern, the credit is given to a Frenchman, Blaise Pascal. It's known as Pascal's triangle, but of course he wasn't the first person to notice it. He just gets all the credit. It was known about thousands of years before Blaise Pascal. I mean, they've uncovered it in ancient Chinese, Aztecs, all coming up with a similar idea. And that pattern starts at the very top with 1, and then we create a triangle, and to get the next row we just add the two numbers immediately above it. So 1, 2, 1, and then 1, 3, 3, 1, 1, 4, 6, 4, 1, and they are indeed the coefficients that we just saw, but that pattern keeps going. There's the expansion for 1 plus x to the power of 5, and then the power of 6, power of 7, 8, 9, and that brings us to my personal favourite, I'm sure it's yours too, power of 10, because it just looks wonderful, doesn't it? I mean, that's just a great pattern when you look at it, because we know the row is symmetric, but then look at the number that's in the middle, 252, that in itself is symmetric as well, but then look at the numbers either side of it, 210, 120, same digits. It's just a wonderful row. As I say, my favourite. You probably have your own. And then we could keep going, and there's power of 11, and I could go again, power of 12, and I'll stop there because I don't know that I could fit 13 in, so we'll just stop there. But it would keep going and keep going and keep going. So if I want to expand out then something like this to the power of 7, I don't have to physically do all that multiplication because I know all of those what we call binomial coefficients. They're the numbers in the row. And then all we have to do is whatever the first term is, 1, it starts at the power of 7 and then just goes down by 1. And then the second term starts to the power of 0 but then goes up by 1. The two powers always adding up to be the power of the binomial, in this case 7. And we can play around with that and we get our answer. There's the expansion. You could, of course, use this. Just imagine you're out and about and you don't have your calculator with you. Oh, damn. But geez, we need to know what 0.998 to the power of 10 is to 8 decimal places. And you'd be there going, how on earth am I ever going to work this out without my calculator? But then you go, oh, hang on. The binomial expansion to the power of 10 would be this. And so if I just let x equal 0.002, I can substitute in. But because I only want it to 8 decimal places, I only need to go up to cubed, because to the power of 4 to 8 decimal places, well, that's going to be 0. And so all those other terms are 0 to 8 decimal places, and I've only got to work that out, and I didn't need my calculator. There it is, 0.980179904. So remember that trick whenever you're out and about and you need to work out something like 0.998 to the power of 10. There you go, maths in the real world. If we want to find the coefficient of x squared in this expression, well, yes, I suppose I could expand the whole thing out, but I'm only concerned with x squared. So really, I just want 2 times this particular term, because that would give me x squared, 6 times 4 squared, 5x squared, but then the minus 3x, I would just multiply by this term, because that would create x squared. I don't really need to worry about all the others. So if I just look at those ones, then I can work out my coefficients. 2 times 6 times 4 squared times 5 squared, minus 3 times 4 times 4 cubed times 5, which is 960. Now, of course, they've asked for the coefficient, so I don't write x squared. It's just the number they're interested in. So 960. Okay. So our first exercise there, I've gone 1 with an asterisk because I've said, well, look, actually we did that in the theory. So when you think about it, why did I bother listing 1? Anyway.